Hi, my name is Ambrosiussen and I work on the game development toolset for Houdini. I build new tools, maintain existing tools, and give Houdini training. In this presentation, we will briefly go over some of the tools found within the game development toolset inside Houdini. The goal of this presentation is to get more developers familiar with it so we can achieve a higher level quality effects and experiences within games, film, and VR. Alright, we're going to do this with the following topics: content generation, content optimization, and getting Houdini effects into game engines. The tools within these topics include Physics Painter, Terrain Tools, Auto UV and Simple Picker, Destruction Cleanup, Texture Sheets and Motion Vectors, and last but not least, Vertex animation textures. So, about the game development toolset. The game development toolset is a series of tools designed to assist the workflow of mainly, but not exclusively, to game developers. It contains shelves, digital assets, custom desktops, and scripts. The toolset is free to download and can be found on GitHub on the following link: github.com/sideeffects/game development toolset. The toolset is being developed and maintained by Louise Cruel, Mike Linden, and myself, Paul Ambrosiussen. The toolset is also a toolset that keeps on developing, and we keep adding and iterating on the already existing tools and making new tools. Some information about the toolset. The toolset is actively being used in production, including in games and VR, film, and any other industry. Also important to note is that the toolset is not tied to Houdini builds, meaning that we're able to do nimble development, meaning that we can push any update to the toolset, any fix, any new tool, whenever we need to. So if someone has a bug and we fix it, we can immediately push this to the toolset, and people can directly download the toolset or the updated toolset to get the fix they requested. The toolset also contains over 60 tools by now in multiple contexts, including SOPs, ROPs, and COPs. On the left you can see some of the tools. All the tools within the game development toolset will all be pushed underneath the Game Dev tab inside the tab menu. If you would like to know more about the game development toolset or would like to see any tutorials of the tools inside the toolset, you can go to the following website: sideeffects.com/learn/game-tools. On this page you will find tutorials not just showing you how to use the tools, but we'll also show you some of the workflows that you can use to use these tools in your pipeline. So just go there and you will see videos about geometry tools, UV tools, texturing tools, real-time effects tools, normal map tools, and interoperability tools. The toolset is also really easy to install. We have three main ways to install the toolset. The first one being an automatic installation. Inside Houdini, when you enable the game development shelf, you will see a button. If you press that button, a pop-up will appear, allowing you to specify which version of the toolset you would like to download. Once you press that and restart Houdini, you will now have the toolset installed for you. You can also go to GitHub and manually download the tools from there and install them in your OTLs folder. If you'd like to see how to do this, you can visit our Vimeo profile, vimeo.com/goprocedural, and look for the video called Game Development Toolset Installation. Alright, so for the first topic, content generation. For content generation, we're going to cover two tools: Physics Painter and Terrain Tools. This topic also provides GitHub examples. So if you go to GitHub and you check the HIP directory, you can find examples for these tools. Did you know that effects HDAs like Physics Painter actually work in Houdini CORE? As long as you author an HDA in an effects instance of Houdini, any user with a core license can both play with it and tweak promoted parameters. So working like this is a cost-effective way of expanding your effects department. So let's take a look at an example of a tool made in effects, but being used in CORE. Physics Painter. So Physics Painter is basically a tool that allows you to paint physics objects onto a scene and then simulate them, freeze those objects, and then once again paint on top of those previous simulated objects. This allows you to build very complex scenes that are physically correct in a really fast manner. This tool, like I said, is also basically a pre-configured .NET, which means that it's core compatible. The toolset also allows you to play with some of the quick settings to get very quick variations. The toolset also allows you to paint low resolution meshes and later on dynamically swap out those with render geometry. Alright, so let's take a look at an example of the tool being used in Houdini. So on the left side we can see my node graph with 3 boxes being merged together, and that will function as a static scene on which I will paint. If I then select my tool, the physics painter, and hit enter in the viewport, we can now see that we get a brush allowing us to paint in 3D on our surfaces of this scene. So in this case what I've done is I've added some leaf models and I'm now going to simulate them. So let's take a look at this tool in action. So first things first, I first configure the tool to generate some variations, so random rotation, some random scale. Then what I do is I assign some objects I want to paint with, in this case low resolution meshes. Then I just simply paint and hit the right key on my keyboard to simulate. Once I find a frame I like, I just press the button dry current paint, freezing the objects that have previously been simulated. And I can keep doing this as many times as I want to produce a result that I am pleased with. So once that's done, what I do is I tell the tool to use a render mesh and replace the low resolution meshes. So as you can see now, I very quickly swapped out the low resolution meshes with render geometry. Once that's done, I now have my final geometry and can either use this to do a render with inside Houdini, or I can export this out to be used in a game development engine. For the next tool, let's talk about terrain tools. So once you've built a beautiful terrain inside Houdini using the height field system, we now need to convert this into a format that our game engine can read and use. So in this case, the tool allows you to do this in 2 ways, which also perfectly work together. We can convert our height field into meshes, and we can convert them into maps. So in this case, the mesh tool allows you to convert the height field into a game-ready mesh. The tool allows you to specify an adaptive density control, meaning that the tool will put polygons on your mesh where it's actually needed. And the user is able to specify where and how harsh this control needs to be. The tool also allows you to automatically generate UVs for your terrain, and is also able to cut up your mesh into tiles. This tool works perfectly well together with the other tool, which is the Game Dev texture tool, which basically extracts common maps of your height fields, such as color maps, height maps, normal maps, cavity maps, and occlusion maps. The tool also allows you to once again cut these into tiles, meaning it works perfectly well together with the meshes we previously made. So in this case, what I'm going to do is I'm quickly making a landscape using the height field system in Houdini. So once I've done that, as you can see, I'm just masking out some areas. I generate a quick road, make some more path in my geometry. So as you can see, we have a combination of some flat regions and some regions that would require more density in polygons if we were to convert this into a mesh. So that's what I'm going to do. Once again, so here we see the final result. So now I'm going to convert this into something we can use. First things first, I convert it into a mesh. So in this case, I specify which layer I want to convert. So in this case, I want to convert the height of the height field into a mesh. And I tell it to use a base density of 0.05, meaning that when in the flatter regions, it's going to use this density. So quite big quads in this case. I also enable adaptive density, meaning that the tool will now look at the curvature of my mesh and figure out, okay, these are the regions that require more polygons to preserve the shape of my mesh. So in this case, I can also remap the density to control how harsh the tool will control where to put the polygons. I can also play with the UVs of the generated mesh. So in this case, I can either decide that it's going to put all the quads from 0 to 1 in total, or I can tell the tool to, for every single quad, do the UV layout from 0 to 1 space, giving us 2 options to work with. Once that's done, I can bring the mesh into a game engine, and I can also bake my maps that I wanted. So in this case, I baked a normal map, a height map, a cavity map, an occlusion map, and told it what resolution I wanted and what the tile size had to be. So in this case, I wanted 4 × 4 tiles. In the bottom right, you can see some of the maps that Houdini generated for me, and I can simply apply those within my game engine. Next up, let's talk about content optimization, making things real-time compatible. So to do this, three example tools that I'm going to show you are Auto UV tool, Simple Baker tool, Destruction Cleanup tool, and once again, these also have examples on GitHub. So to begin with, the Auto UV and the Simple Baker. These two tools allow you to generate quick and easy UVs and allow you to do map baking from high resolution to low resolution meshes as easy as 1, 2, 3. The tool supports common maps by default, such as vertex color, normal map, roughness map, metallic map, world normal map, AO maps, curvature, thickness, position, and height. The tool also allows you to specify any custom maps you would like to build. And once the tool has finished baking, it will load back these textures and apply them to your mesh within the viewport to give you a really quick preview. Here we see an example of a decimation pipeline. In this case, I had my source file with 3.2 million triangles, and I baked it down onto a mesh which I generated using the Auto UV and the polyreduce tool of 10,000 triangles. As you can see, the tools do a really good job at preserving details. Alright, so this is an example of the Auto UV tool. So in this case, I simply fed it the mesh. I played around with some sliders, which didn't take a long time, maybe a minute or so, and then it gave me a really nice result, which I can use to bake maps of. So if you compare a traditional decimation pipeline with a new pipeline, this is what a regular decimation pipeline looks like. We begin with our high resolution source mesh, which can come from ZBrush or a photogrammetry pipeline or any other source. We bring it into a DCC such as ZBrush or Topogon or Maya or Max or any other application. And there we need to do a manual retopology of our high resolution mesh. Once we've done that, we need to generate UVs for these. So we can either stay in the same application or we can bring it into a different application such as UV Master or Unfold 3D. Once that's done, we now have our low resolution mesh and we have UVs on those. So what we need to do is we need to bake our high resolution mesh onto our low resolution mesh, and most of the times this is being done in a different application such as, for example, Knald or Substance or Marmoset or XNormal. Once that's done, we bring it into our texturing application, which can be Substance or Quixel or Photoshop or any other application, and once that's done, we can export it and bring it into a game engine. So what we can see here is that we're going to jump between at least 5 to 7 different applications, meaning that there's lots of time spent on switching between application. If we then want to reiterate on something, we need to go all the way back and do all the steps that come afterwards again, meaning that we spend lots of time doing that, which is a waste of time. So what if we can do all of that within one application? Well, in this case we can. Houdini. So we bring in our high resolution source mesh, which can be done using the Go Z bridge from ZBrush or using the now integrated reality capture plugin. Once that's done, we can automatically generate a game resolution mesh using the voxel mesh and then plug it into the polyreduce or instant meshes. Once that's done, we plug it into our Auto UV tool, which generates nice UVs for you. We can tweak it if you want to using the UV flatten and the UV layout tool. Once that's done, we plug it into the Simple Baker to bake any maps we need. And then we can go to the COPS context to generate some nice textures for us and do the shading of our mesh. And then we can just export it as FBX or use any other sort of exporter to bring into a game engine. So this means that we can do all these steps within one application. Let's take a look at how that looks like within Houdini. So in this case, we bring in our file, and the first thing we do is we voxelize it, meaning that we take our geometry and convert it into a volume. We do this to get rid of any bad geometry that we might have, because a volume is not really directly linked to your mesh. So once that's done, we convert it back to a mesh to give us a nice starting point. And we're going to either optionally paint an attribute on there to tell Houdini where we want to have a higher density of polygons, or we can also automatically generate this data by figuring out what the curvature is. We then plug it into our polyreduce node, which is going to reduce our poly count to the goal or the target we've set for ourselves. Once that's done, it automatically flows through to the Auto UV tool. giving us some nice UVs. Once that's done, optionally, we can tweak or make some adjustments to our UVs, and then we automatically plug it into our simple baker, doing the map baking for us. So the really nice thing about this is that we have a non-destructive workflow, meaning that we don't need to jump between applications. If we change something upstream, everything underneath it will also automatically update. Another nice thing is that we only need to build this graph once. So since I've already built it once, I can now simply change the source file at the top, and we will now get our new low resolution mesh with all the baked textures. Once again, you can find this file on GitHub. Next up, destruction cleanup. You can do beautiful destructions within Houdini, but often these are not yet game ready in terms of overhead. So in this case, what this tool does is you simply plug in your geometry, you plug in your simulation, and the tool will figure out what are the actual transforms you need and which one can it bake together. So it does an optimization of the transform count, meaning that depending on how you export it, if you, for example, export it out as bones, you will get fewer bones while maintaining the quality you had in your original simulation. It also automatically cleans up your geometry. So if you have pieces that are sticking together, it will also automatically remove any polygons you don't see. And the tool also offers you two different ways of cleaning up, which is a constraint versus proximity cleanup, which really depends on what kind of data you can feed the tool. So you tell it what the simulation range is. In this case, I want to do my full frame range from frame 1 to 240. And I change some parameters, giving me what I need. So in this case, let's compare. This is my starting file. So as we can see, lots of these pieces either don't move in the simulation, or some of these actually stick together while flying through the air. So in this case, we can see this orange and bluish piece, they actually stick together, meaning that we can definitely merge these together procedurally. So let's see how easy it is. I simply plug in my tool, and as we can see now, it already cleaned it up for me. So in this case, all the pieces that initially or don't move at all in my simulation are now batched together into one transform, meaning that we have way less overhead in the game engine. So let's take a look at an example of an extreme case. So in this case, I have this wall which is being fractured using a Voronoi fracture, and it starts off with 2000 packed primitives. After running it through the tool, which analyzes what happens in the simulation, we only have 59 pieces, meaning that we have a massive reduction without doing a lot of manual cleanup. It does it all for us. It also reduces the amount of polygons, because all these inside faces that you don't see because the pieces stick together have also been removed. So we went down from 27,000 to only 5,000. Same goes in terms of memory. We reduced it from 1.9 megabyte down to 60.2 kilobyte. So using this tool is really easy and allows you to optimize your simulations really fast. And it also allows you to keep iterating on your simulation without having to lock something down after cleaning it up. Next up, texture sheets. How do we get Houdini effects into game engines? We're going to talk about texture sheets, motion vectors, and vertex animation textures. Once again, these tools also have examples on GitHub. To begin with, texture sheets. Texture sheets allows you to basically take any pyro simulation you have and automatically generate texture sheets from these, which include the color maps, the normal maps, and also allows you to pack these together so we only have one texture atlas to work with. So all we need to do is we need to tell the tool which node to render and which camera to use. Once we have that, we specify where we want our textures to be exported to, and we tell it how many frames and at what resolution. Once that's done, we simply hit render sequence and we get a nice result. So that will give us some data which allows us in-engine, in the shader, to tweak to get a result we want. So in this case, since we split the different channels, such as, for example, emission into a separate channel within the texture, we can now keep changing this within the shader without having to update our texture. The tool also bakes normal maps of these, meaning that we can even relight them inside the engine. So this is a really nice example made by Haodong Wang, who basically used our tool to generate this beautifully looking explosion and brought it into a game engine, which allowed him to play it back. If you'd like to see more of his work, you can visit his profile on vimeo.com/HaodongWang. So we have a nice pyro simulation, but we want to make it even better. So what we can do is we can use something called motion vectors. Motion vectors basically looks at your pyro simulation and generates motion vectors, describing what the motion is within or between frames in a texture atlas. So this allows us to retime our flipbooks and can even reduce the number of required frames if we want to play something back in slow motion, meaning that we can also do smooth playback. Once again, we specify a frame range, tell it which node to export, which camera to use, and the resolution we would like to use. Here we see a comparison between a simulation being played back inside an engine in slow-mo with no motion vectors applied and one with motion vectors applied on the right side. So as you can see, it's really smooth without increasing the number of frames we need to get this nice playback. So this allows us to get a high fidelity playback without requiring us to render out a crazy amount of frames. Next up, Vertex animation textures. So Vertex animation textures is a really nice tool that allows you to basically export out any geometry animation or vertex animation using either one of four modes. So in this case, we can use a soft export, which requires the simulation to keep a same topology. So think of a cloth simulation. We can also export out a rigid simulation, meaning that, for example, we take a rigid body dynamics and we export it out. Think of a fracture. We can export out fluids. This is an important one because we can basically bring an vertex animation with changing topology into a game engine, which is really difficult to do. Or we can either decide to go with a sprite camera facing cards export, for example, for any particle simulation. What we need to do is, once again, we specify which node we want to export. So what is the animation we want to export? We play with some texture size to allow the user to specify what size texture he wants. We allow you to export the geometry and an EXR file. You specify what the frame range is you want to export and which attributes to use to export it with. Once that's done, it's basically going to generate three files for us. It's going to generate an FBX file and two EXR files. The FBX file is basically a cloud of triangles that we are going to displace within the shader in a game engine, and the EXR basically is a texture that describes what the motion is for every single vertex. The important thing to note here is that this is a tool that not only works with Unreal or Unity, it's basically a format that allows you to build this system into any engine. So not just the custom engines, but also your proprietary engine. The only thing you need to do is replicate the shader that we've also provided you with, and then you can get the exact same playback inside your engine. So as you can see, we can have a fluid simulation on the right, we can do a pyro simulation being meshed, we can do a cloth simulation, we can do a fracture, and we can even do particle systems. So this allows us to do a really highly art-directable effect and bring it into our game engine and play it back at any speed we would like. Here we see an example of a blood effect made by Andreas Glad, aka Partikel. In this case, it's an effect that's highly art-directable, being made inside Houdini and being exported using the Vertex animation textures. So you get the exact same result you had in Houdini in your game engine after you've done some tweaks to your material and shader. If you'd like to see more of his work, you can visit his Vimeo profile on vimeo.com/partikel. Here we have another example of two fluid simulations being made inside Houdini, being exported out and being played inside a game engine. So in the middle, we can see a nice fountain. We did a fluid simulation and then meshed it and brought it into engine. On the right side, once again, another fluid simulation, which is also being played back inside a game engine. These are also made by Haodong Wang. So, to conclude this presentation, these tools I showed you are only the surface of the game development toolset. So now you've seen some of the things contained within the toolset. We would like to invite you to download it for free from GitHub and build some awesome content with it. If you have any questions, feel free to reach out to Luis Cruel, Mike Linden, or myself. Have fun!